In today's session, I will be discussing about the stresses on oblique planes due to biaxial forces. And the previous lecture we have discussed about uniaxial stresses, and due to that, what are the stresses on oblique planes? So we have seen direct stresses in the beginning. Now we will see the stresses on an oblique plane due to biaxial forces acting on a mass. So now we consider an object subjected to biaxial stresses sigma x and sigma y as shown in the figure here. Okay. So due to that, what will be the stresses on the inclined plane or oblique plane AB, making an angle theta with x axis. Okay. So for that, we will consider the free body diagram of the portion ABC, and here we consider unit dimension perpendicular to the plane. Okay, unit dimension perpendicular to the plane of the object. So if you consider the portion ABC, the forces acting on AC, that is sigma x. Stress acting on BC is sigma y. Okay, on the portion BC, it is sigma y. So what will be the forces acting on AC and BC? Force acting on AC is sigma x into area of face AC. So here AC is one dimension, the perpendicular dimension is 1 unit. So AC into 1 will be the area here of this face. So the force acting on the face AC is sigma x into area AC into 1. Okay, AC into 1. Now the force acting on BC, the force acting on BC is sigma y into area, sigma y into area of the face BC. What is it? BC into 1. So the force acting on the face BC is sigma y into BC into 1. Okay. So now, what will be the forces acting on this? Okay, inclined plane. So for equilibrium, we know that we will have the force P x and Py. Say this is Py and what we have assumed it P1 and P2, I think Px and Py. Yeah, Px and Py here. Okay, for equilibrium of this portion ABC, you should have forces Px and Py acting upward and towards right. Okay, now these forces acting on face AB will be resolved along the normal to the face AB and tangential to the face AB. Okay, we find the normal component of these forces and tangential components of these two forces in on face AB. Okay. So what will be the normal and tangential components? Okay. So what will be the normal component here of this force Px? Here you observe this angle is theta. So this will be 90 minus theta. Okay. And this will be theta again. So this is 90 minus theta. So normal component of Px is Px cos 90 minus theta. And you have normal component of Py also. Normal component of Py, isn't it? And both are in the same direction, away from the face, isn't it? So Py cos theta. So Px into cos 90 minus theta is Px sin theta plus Py cos theta. That is the normal component of force. How about the tangential component? Pt. This is Pn. So the tangential component is, if you observe, the tangential component of Px is acting downwards and that of Py is acting upwards. So we have to find the net tangential force by subtracting Px cos theta, this angle is theta, minus Py sin theta. So this is the tangential component of the forces, net tangential component acting on inclined face AB. Now let us see that. Okay. First thing, Px is force Px. This is A, C, B, isn't it? So Px is stress in x direction is sigma x multiplied by area, as we have seen, AC into 1. And Py is sigma y into BC, isn't it? This area. That we have seen. And now the normal component, as we have discussed now, the normal component of force, which is Px. This angle is theta, so this will be 90 minus theta, because this are equal, theta. So Px cos 90 minus theta or Px sin theta and Py cos theta. That we have seen, just now discussed. Px sin theta plus Py cos theta. This angle is theta. Okay. So the total normal component is sum of these two, because both are in the same direction. We have to add. Algebraic sum we will take. Similarly, the tangential component, Px cos theta minus Py sin theta. And you replace Px and Py by sigma x AC and Py is sigma y BC. Similarly, you replace here. Okay. Now, knowing this force, what will be the stress on AB along the normal component of stress? So, sigma n is Pn by area AB into 1. Here also the perpendicular dimension is 1 unit. So Pn by AB. Okay. So this divided by AB. Understand? Sigma x AC sin theta. No, sigma x AC sin theta plus sigma y BC cos theta divided by area AB. Now we split this, sigma x into AC by AB. What is AC by AB? This is theta. A, C and B. So AC by AB is Sin theta, isn't it? AC by AB. Sin theta is AC by AB and cos theta is BC by AB. So AC by AB is sin theta. So sigma x sin theta into sin theta, that is sigma x sin square theta. Sigma y into BC by AB is cos theta. Okay. So cos theta into cos theta, that is cos square theta. Okay. So this is the normal stress, sigma x sin square theta plus sigma y cos square theta. So in a member which is subjected to biaxial stresses, sigma x and sigma y, the normal stress on an inclined plane is given by this expression. Okay, sigma x sin square theta plus sigma y cos square theta. And it can also be shown like this by taking sin square theta as 1 minus cos 2 theta and cos square theta as 1 plus cos 2 theta by 2. Okay, so 1 minus cos 2 theta by 2 and cos square theta is 1 plus cos 2 theta by 2. Okay, splitting and rearranging, we will get sigma n equal to sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 into cos 2 theta. Okay, minus of sigma x minus sigma y by 2 into cos 2 theta. So this is the normal stress on the inclined plane. Okay, normal stress acting on the oblique plane, making an angle theta with x direction. Okay. Similarly, we find tangential stress sigma t as Pt by area AB, because the tangential stress sigma t or tau, we can write sigma t or tau, generally we represent it by tau. Tau is equal to shear stress, tangential stress or shear stress, which is equal to Pt by A. So what is Pt? Already we have seen here. Pt is sigma x AC cos theta minus sigma y BC sin theta, isn't it? So that divided by, this is Pt, divided by AB. Again, AC by AB is, what is AC by AB? Sin theta, isn't it? AC by AB is sin theta and BC by AB is cos theta. So sigma x sin theta cos theta minus sigma y sin theta cos theta. So you can also write this as sigma x minus sigma y into sin theta cos theta, which is sin 2 theta by 2. So sigma x minus sigma y by 2 into sin 2 theta. This is the shear stress acting on oblique plane AB. Shear stress acting on oblique plane AB. Understand? And now we will see for what angle the shear stress is maximum and normal stress is maximum. Already we have seen the principal planes definition, isn't it? The planes on which the shear stress is 0 and there will be only normal stress acting. They are called principal planes. So we can locate principal planes also now by using the definition. So here we have seen tau is equal to sigma x minus sigma y by 2 sine 2 theta. So for principal planes, tau should be 0, isn't it? Shear stress should be 0. So for what value of theta? Because sigma x cannot be 0, sine 2 theta must be 0. So sine 2 theta is 0, or theta will be 0, or it can take 90. Okay. So theta 0 means this plane. Theta 0 means this plane. So what will be the normal stress acting on this plane when theta is 0? Sigma y. Similarly, when theta is 90, this plane, and the stress acting will be sigma x on this plane. Okay. So here sigma x and sigma y are the principal stresses. In this particular case, sigma x, sigma y are the principal stresses, and these planes are principal planes. Understand? And for what inclination theta, you will have the shear stress maximum. For that, sine 2 theta should be maximum. And what is its maximum value? 1, isn't it? Maximum value is 1 or minus 1 on the negative side. So when for tau should be for shear stress to be maximum, sine 2 theta is 1, and maximum shear stress will be sigma x minus sigma y by 2. Okay. And what is theta? 2 theta is 1 sine inverse, that is 90 or 270. Okay. So theta will be 45 degrees or 135 degrees, like that. Okay. So when theta is 45 degrees, you will have maximum shear stress on the plane AB. Okay. Understand? And for any inclination theta, the resultant stress sigma r acting on AB will be given by this expression. Because these two are rectangular components, the resultant will be given as square root of sigma n square plus tau square. Okay. That is the resultant stress, and its inclination with normal or with tangent we can find. Okay. With the normal, if you want the inclination alpha, tan alpha is given as tau by sigma n. So this gives the inclination of resultant with the normal stress. Inclination of resultant with normal stress. Okay. Yeah. So that's how we'll find out the stresses on an oblique plane when the body is subjected to biaxial stresses. Biaxial stresses. Both are tensile here. One of them may be compressive, or both may be compressive. When it is compressive, we will take negative sign in this expression. Okay. If sigma x is compressive, then we will take negative sign here. The expression is same, but we will take negative sign if the stress is compressive. Okay. We have derived this assuming that the stresses are tensile. Okay. In case if the stresses are compressive, then we will take negative sign, opposite sign. Is this clear? Yeah. Now let us see some examples. Here the problems will be solved by direct substitution only, because we know the formula. Okay. Knowing formula, we can find out the normal and shear stresses just by substitution. Okay. So here, what is given is, you can read it. A point in a strained material is subjected to two mutually perpendicular tensile stresses. Tensile stresses. So one is 200 megapascals Newton per mm square, megapascal means. And the other one is 100 megapascals. Okay. So determine the intensities of normal and shear stresses and resultant stress on a plane inclined at 30 degrees with the axis of minor principal stress. That is important. Of these two, which is minor, 100 is minor, isn't it? The least is 100, minor principal stress and major principal stress. This is minor principal stress and this is major principal stress. The least one is called minor principal stress. Okay. So inclined at 30 degrees to the axis of minor principal. This is the axis of minor principal stress. So the plane is inclined at 30 degrees to this. This inclination is 30. So what will be this? 60. Okay. If this is 30, this will be 60. With major principal stress, the angle is 60. So we are assuming this as sigma x and this is sigma y, say. And we have derived the formula taking the angle theta making with sigma x. Angle theta of inclined plane with sigma x direction. So we will consider this angle as theta. Okay. And now how to find sigma n? Direct substitution here. Sorry, this is something wrong. This value is something wrong. It is 200. Okay. So here sigma n is now, what is sigma n? Formula for normal stress, sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 into cos 2 theta. Okay. Yeah. So here sigma x is 200. 200 plus 100 by 2 plus 200 minus 100 by 2 cos 2 into 60. Okay. So that gives normal stress, and shear stress is sigma x minus sigma y by 2 into, actually this should be 60. Okay. You can make, because when you are considering 200 as sigma x, then the formula will be angle theta will be with sigma x direction we have to take, that is 60. In the problem, what is given is the inclination with minor principal stress, that is sigma y. With sigma y the angle is 30. So this is 60 we have to take. Accordingly this will change and this also will change. Okay. So what you need to concentrate here is the angle theta is with x direction. Okay. That you have to be careful. Yes. Next, another example we'll see. The stresses at a point in a component in a member are 100 Newton per mm square tensile and 15 Newton per mm square compressive. One of the stresses is compressive. So, this is 100 tensile and 50 compressive. Let us take sigma y. Yes, 50 Newton per mm square and sigma x 100 Newton per mm square. Okay. So, determine the magnitude of normal and shear stresses on a plane inclined at an angle 20 degrees with tensile stress. It is tensile, compressive stress. So here 25 degrees theta with tensile stress. That is important. That means with 100 Newton per mm square, the angle of inclination is 25. Theta is 25. Also determine the direction of resultant and the magnitude of maximum shear stress. So here the normal stress is calculated first. Sigma x is 100 Newton per mm square. Sigma y is minus 50. Minus is here because of direction, compression. Okay. So when you substitute sigma y here, we will take minus 50 because it is compressive. Okay. So sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 into cos 2 theta. Okay. So here 100 minus 50 by 2, that is 25. And this one 100 plus 50 by 2, 75 into cos 50. Okay. That comes I think around 48.21. The resultant of this is minus 23.21. What does this mean? Normal stress is minus, means it will be acting towards the plane AB. Sigma n is towards, because we have assumed sigma n acting away from the plane, but here it is towards. This means it is compressive. Compressive stress acting on AB. Normal stress is compressive. Similarly, we can find the shear stress as sigma x minus sigma y by 2 sine 2 theta. So which is coming around 57.45. Okay. So on this inclined plane, now we have sigma n and sigma tau. So tau is acting downwards. Say. What will be the resultant? Resultant stress. Yeah, this is resultant stress, sigma r, which is obtained by this. And what is the inclination of this with the normal? Tan alpha. We will find tan alpha as tau by sigma n. This gives alpha. The direction of resultant force. Inclination of resultant force. And what is the maximum shear stress? Maximum shear stress will be direction is 68 degrees. And how about normal maximum shear stress? 75. Sigma x minus sigma y by 2. 75 megapascals. Okay. Yeah. So these problems can be solved by graphical method also. We will discuss that in the next session. That is by using Morse circles. We can solve these problems. We can find the normal shear and maximum shear stress, everything we can find by using graphical method, that is Morse circle method. And before that, we have to discuss two more cases. That is when the object is subjected to, when the member is subjected to pure shear. Okay, what will be the stresses acting on inclined oblique plane? Similarly, when a member is subjected to normal stresses as well as shear stresses. Okay, sigma x, sigma y, and tau. Yeah, these two cases we will discuss in the next session. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.